All right, so I wanted to take a look at the homework problem because this is really going to be related to the appraisal that you're taking either Tuesday if you are period E or Wednesday if you are period A and D. So really go over this homework, study this appraisal because this is really what I want to appraise on. And I actually want to take a look at both problems in this. So we're going to be covering work, energy, and conservation of energy, and then we're also going to be covering momentum and impulse. So we have a dart gun that vertically launches a dart 0.5 meters high. If the spring in the dart gun is compressed 0.04 meters, what is the spring constant? So first of all, one thing I notice that people do is that they just read this and they immediately just draw, oh, there must be initially gravitational energy, and then later there's a spring, and they just don't think about what's going on. So I want you to just stop for a moment and actually read the whole question from beginning to end and try to picture what this scenario is. And what I'm hoping, this is my ideal, is that what you'll picture is a dart gun with a little dart here compressed as the initial, and then as the final, we have that the dart gun is fired and the dart is actually up here. So this is final, and this is initial. And so we actually begin with all elastic energy, and we wind up with all gravity energy at the end. So actually our equation is going to be E elastic equals E gravity. In other words, we're going to have 1/2 kx squared equals m times g times h. And now let's put in our numbers. So we have 1/2 times our unknown k. And the compression of the dart is 0.04 meters. Don't forget to square that. That's going to equal 0.025 times 10 times the height that we actually finally get to. Now what I don't want to do is every line of algebra here. So I'm going to go ahead and actually just tell you what the answer is, and it's going to be up to you to actually check the arithmetic there. So what we're going to end up getting for k is 156.25 newtons per meter. Now we ask a second question, which is, well, suppose we compress the dart gun by the same amount again, but now the dart only goes 0.4 meters high and we want to get the dissipated energy. So once again, we start with all elastic energy, but now what happens is that we get some of our height and the rest of the energy is actually dissipated by air resistance. So we're going to end up getting here 1/2 times, you know what, let's be really clear, E elastic equals E gravity plus E dissipated. And working with that, let's plug in our numbers. We're going to end up getting here 1/2 times 156.25, which is K, times X, which is 0.04 squared, equals M, which is 0.025, times G, which is 10, times the height, which is now 0.4 meters. And then the leftover that we have is just the dissipated energy. So I'm going to plug in the numbers, and when we actually calculate E dissipated, we're going to end up getting 0.025 joules. Now, what this means is that the work done by air resistance is exactly equal to the dissipated energy. Remember, work is the means by which energy is transformed from one form to another. So the work done by the dissipated energy is going to be the work done by the air resistance is equal to this dissipated energy because we've transformed some of our elastic energy into dissipated energy. So that's going to give us 0.025 joules. Now, if we want to get the average force of air resistance, now we use, and you know what? I'm going to use the Wonder Woman W for work. So the average force of air resistance is going to be F times the x, the distance over which it acted. So we know we have 0.025 joules of work times equals the force times the distance over which it acted, which is 0.4 meters. So the actual air resistance force is going to be 0.025 divided by 0.4, and when we work that out, that fraction is going to reduce to 25 over 40, which is going to be 5 over 8, which is about 0.51 newtons worth of force. So that's the first part of the homework, and in the second video, I want to go ahead and do the impulse momentum problem.